In this short video, we're going to see the origins of an important equation in electrochemistry called the Nernst equation. It actually comes from a little bit of dimensional analysis and a couple of equations we've seen already in other videos in the sequence of videos. So we're going to recall a couple of equations. The first thing we want to recall is previously we've said that electrical potential energy is the product of the charge of an electron and the voltage that the electron finds itself in the presence of. So we've previously seen this equation in an earlier electrochemistry video, and we're going to recall it here. If we do a couple of things with this, first of all, we can scale this to a mole. Right now we just have the electrical potential energy for one electron in the presence of a voltage. What if we scale this to a mole's worth of electrons? So we can say let F equal essentially Avogadro's number, so we'll call it Na lots of E. So let F equal Avogadro's number of electric charges. So if we looked at units, instead of having coulomb for electron, we would have coulomb per mole for a mole's worth of electrons. And F here is just Faraday's constant. It has a value of 96485 coulomb per mole. So this is probably a number worth remembering for any assessment at the general chemistry level of electrochemistry. So we can say that our electrical potential energy is now, instead of just one electron, we've scaled it to a mole's worth of electrons times by voltage. So here we've just scaled by Avogadro times by the voltage. So we've normalized per mole, but what if I have fractions thereof? What if I have fractions of a mole, multiples of a mole? So at this point I want to take the normalization per mole and then scale it to a number of moles. So we know that mole is the symbol N, so we can say that the potential energy is however many moles I have, the charge per mole times by the voltage. And then recall that by definition, potential energy tends to be, by definition, negative of other types of energy. So for example, an increase in kinetic energy is the equivalent decrease in potential energy. So let a positive potential energy be proportional, or rather a change in potential energy be proportional to a negative change in another type of energy, and the type of energy we're interested in is going to be Gibbs free energy. So we have this change in sign. Obviously I want to write with respect to a positive change in Gibbs free energy. So this idea that potential energy is for the most part negative with respect to other types of energy, we can rewrite this as, instead of a positive relationship, if I rephrase that as Gibbs free energy change, I could say negative NFV. For the most part, we're done. However, in a lot of general chemistry textbooks, V is rewritten as E for electromotive force. So for the most part, you'll see this equation written like this, where delta G is minus moles, N, Faraday's constant, F, voltage or electromotive force, E. We can have delta G under non-standard conditions. or we could definitely have delta G under standard conditions, in which case we would just add the standard conditions to the voltage. Okay, so we're going to use this equation in a second in our drive towards the Nernst equation. So I'll clear the board, we'll rephrase this equation and a second equation, and then we'll go ahead and produce the Nernst equation. Okay, in the previous board we saw an origin of this equation. In a previous video we've seen an origin of this equation in a thermodynamics video in this sequence. So essentially we've got an ability to substitute into this equation, instead of delta G, we can substitute in minus NFE without standards for this delta G and with standards for this delta G. So we combine these two equations, we can clearly see that delta G without the standard, which is just minus N Faraday's constant E without the standard, is equal to minus N Faraday's constant E with the standard, and then plus RT log Q. Remember that Q is just the reaction quotient. It means it's a law of mass action, but it's not a constant value. So we have this expression here. If I want to isolate the voltage, I would just divide through by minus NF. So I'm going to divide through by minus NF. So I have minus NFE divided by minus NF equals minus NFE standard divided by minus NF plus RT log Q divided by minus NF. So I'm dividing through my expression with minus NF. I do want to point out at this stage, because we're looking at Gibbs free energy, both of these expressions are the second law of thermodynamics. So everything on this board, again, it's important to keep in mind, we're just looking at the second law of thermodynamics. So in that vein, electrochemistry just becomes a way to study, a practical way to study the second law of thermodynamics. If we actually do this calculation, the minus NF cancels, the minus NF cancels, and we get left with the voltage under non-standard conditions is equal to the voltage under standard conditions. The negative in the denominator supersedes this negative, this positive, and makes the overall correction factor here a negative, and we have RT log Q over NF. And this is how it will be presented to you in a textbook. This is the Nernst equation. You'll notice it's essentially exactly the same equation here. In fact, if we compare them, there's absolutely no difference between these equations. We've got a variable under non-standard conditions is equal to a variable under standard conditions plus or minus a correction factor to the equality. You can see that this is a y equals mx plus b equation. So you could plot this on a straight line graph. You could use a data spreadsheet to quickly ascertain these values, and essentially in a homework type question, Excel and a straight line y is mx plus b graph becomes a useful tool. Obviously in an exam where you don't have Excel, you would just pick two values, connect them, you know they should be a straight line, connect them, and then you can get the slope and then move forward from your values. Before we clear this board, when would you use the Nernst equation? Well, as you can see, you would use the Nernst equation if you're trying to calculate non-standard voltage. So clearly, standard conditions assumes 25 degrees Celsius. Non-standard conditions would assume something other than 25 degrees Celsius. It could also be concentration changes. So standard conditions assumes 1 molar solutions. Non-standard conditions assumes that the anode and cathode in the cell have other than 1 molar solutions. And in general, for the most part, in general chemistry, when we say non-standard conditions, we don't really mean non-standard temperature, although that would be perfectly fine. We assume non-standard concentration. That seems to be a more common way to enforce non-standard conditions. And as you might expect, people nowadays almost always have a cell phone, and you're very aware that your cell phone shouldn't be left in a hot car. It can affect the battery life or the operating conditions if your cell phone overheats. Well, clearly the voltage when the temperature changes is different. So when appliances are manufactured, the fact that the voltage supplied from a battery changes with environmental conditions has to be tolerated by the appliance itself through capacitors and what have you. But this essentially will tell you that there's a temperature sensitivity to voltage, as you might expect from consumer appliance media. Okay, so again, this is the Nernst equation, almost identical to this canonical Gibbs free energy equation, because both are exactly the same thing. Both are the second law of thermodynamics. How about we look at the Nernst equation at equilibrium? So if we start to look at the Nernst equation at equilibrium, let's start off with the Nernst equation. So the voltage under non-standard conditions is the voltage under standard conditions, minus RT, the ideal gas constant, temperature over moles, Faraday's constant, log the reaction quotient. So this is the Nernst equation. At equilibrium, well, first of all, we know that at equilibrium, then the non-standard voltage is 0, and we know that, because essentially equilibrium for a battery would mean a flat battery. It means that the chemical reaction is finished. There's no net driving force forcing the electrons to move. So there's no voltage at equilibrium. We also know that Q becomes K at equilibrium, the equilibrium constant. So we can say that 0 volts is the standard voltage minus RT over NF log K. Okay. If we transpose the negative term over to the other side and make it positive, we can say that the standard voltage is positive RT over NF log K. If we wanted perhaps to find out what the equilibrium constant is, we can isolate that and say that the log of the equilibrium constant, we could just take this term over here. So the NF would go up here. So it would be NF E standard voltage, and then the RT would come down here. Well, we can see that this term here is minus Gibbs free energy. So we can say that that is minus the standard Gibbs free energy change over RT. And if we wanted to isolate K, we would take exponents of both sides. So we could say that K, the equilibrium constant, is e to the minus standard change in Gibbs free energy over RT. Okay, so whether we have this expression or we have, which we can see as a Boltzmann style decay, it's an exponential decay that's related to energy and temperature. So it would follow a Boltzmann style decay. Or if we take the logarithm of both sides and we have essentially as a y is mx plus b type equation, which is what we started with here, then we have access again from the electrochemistry back to the thermodynamics. And so as you can see, typically although thermodynamics is encountered earlier in a course, a general chemistry course, than electrochemistry, you're really stunted in your thermodynamics discussions without electrochemistry because both are allowing you access and agency to study the second law of thermodynamics. So you can absolutely use some electrochemistry concepts to go back and readdress some more thermodynamic concepts because they're really the same thing. In this part of the video, I want to extend our look at the Nernst equation to investigate the variation of voltage with pH. This has, as you might predict, a lot of biological and biochemical implications linked with normal cellular behavior and then pathological behavior. So for example, let's consider a biological reaction from the Krebs cycle. So if we have this equation, so this chemical is fumaric acid. Your ability to draw this chemical is irrelevant. We're just going to label it because it's a biological process. So fumaric acid with 2 protons and 2 electrons. And if you, like me, know that really you should write hydronium ion, feel free to do that. If you don't like 2 protons, we can always write 2 hydronium ions, that's fine. You can always just add the water after the fact if you like. So this would give succinic acid Again, the structure is irrelevant, but see that we have an addition across this double bond. We've gone from this double bond structure in the presence of acid to a single bond structure. And we want to know, clearly it's a redox process. Clearly it's a pH sensitive process because we have acids involved. And we want to see, because it's an electron transfer process and essentially can be manipulated via voltage, we want to see what the voltage sensitivity is. Okay, so let log of x equal log of 10. Now notice I've got log base e of x. Let log base e of x equal log 10 multiplied by log base 10 of x. Okay? So we're calling on some log rules here. And you can see here, if you look at this part of the structure, we have log base 10 of 10. Well, by definition, that equals 1. And we're left with just log x multiplied by 1. So we're going to use this assertion here moving forward. Okay, so this implies that log base e of the hydronium ion, so you can either write hydronium ion here or just a proton if you have the proton, is equal to log base E10 and then log base 10 of the hydronium ion. Okay, so by definition, log of base E of 10, log base 10 of x, where x is our hydronium. And this is equal to negative log of 10 multiplied by the pH. And we can see here from our acid-base discussions that log base 10 of hydronium, so recall what pH was. pH by definition was minus log base 10 of the hydronium ion concentration. So I've only got positive log base 10. So instead of that being the pH, that's the negative pH, and we just put the negative outside here. So I've essentially got a negative pH, but I can just look at the positive pH and have the negative over here. So this is fiddly. It's something you want to look at a few times. So we've got this new assertion just from using a log rule. If we look back at our initial equation, which is part of the Krebs cycle, we've got fumaric acid, we have electrons as reactants, so that must be a reduction reaction. So this fumaric acid is being reduced, we're adding hydrogen to make succinic acid. Essentially, the only thing that's really important in dynamic equilibrium, we'll assume, is the protons themselves, or the hydronium ions. So if we look at the reaction quotient, I know that if I'm only interested in the pH effects, then my hydronium, which is essentially responsible for my pH, so let the H in pH mean hydronium, then it's going to be a denominator in my reaction quotient because it's a reactant in my reaction profile. Remember that products become numerators, reactants become denominators. I've got a coefficient 2, so the reaction quotient is going to be 1 over hydronium squared. Again, why is the hydronium a denominator? The hydronium is a denominator because the hydronium is a reactant. Why is there an exponent 2 here? There's an exponent 2 here because there's a coefficient 2 here. So I'm going to clean the board up. We're going to use the Nernst equation. We now have Q, and we're going to plug in this Q into our Nernst equation. So I've tidied the board, I've reiterated my reaction quotient, 1 over hydronium squared. I've restated my Nernst equation. I'm now going to insert Q into my Nernst equation. So I've got the voltage is the standard voltage minus RT over NF. And then I've got log Q, which I can state as log 10 Q. Okay, so remember, essentially from earlier, my log x, my natural log x is natural log 10 log base 10x. So I can replace this log Q with my little log rule from earlier. And I can say that this is equal to E standard minus RT over NF log 10 log 10 Q, where Q is 1 over hydronium squared. Okay, so I've just inserted Q into my log Q expression here. From my log rules, I know that positive log of any base of x is equal to negative log of the same base 1 over x. So again, whenever I take the inverse argument logarithm, I change the sign of the argument. So I'm going to flip this fraction to make it hydronium, and then I'll incur a negative sign because originally it's a positive log. That negative sign I'm just going to bring over here and trip this to be positive. So this is E cell positive RT over NF log 10 hydronium squared. Again, I've used this log rule here. I've flipped this, taken the inverse of this argument here, incurred the negative sign, where I brought the negative sign over here, and tripped this negative sign to make it positive. I'll clean this board, we'll continue our discussion momentarily. Okay, so we left off in the previous board with this expression here, so let's continue. Let's put values of n back in now. We know from our equation here that n, the number of moles of electrons, is 2. So we can put that in. So we have E under non-standard conditions is E under standard conditions plus RT over NF. Well, here n is 2. So 2F. But then also, we can do something about this coefficient, this exponent 2 here. We know from our log rules that log of any base x squared is just 2 log to the same base of x. So with logs we can write exponents as coefficients. So let's go ahead and bring this exponent 2 down as a coefficient. And we'll put the coefficient here, outside of the parentheses here, log 10, log base 10 hydronium. So again, we've used this rule of logs to bring that exponent down as a coefficient here. And now you can see that this 2 will cancel this 2. So we've got, and there should be a standard there, E standard plus RT over F log 10 hydronium. Well, this is positive log 10 hydronium. I want the pH, so I need to multiply both sides by a negative. I need to make this negative. Let's write the negative here. So I can write E is E standard minus RT over F log 10. I put the negative there, so that just becomes pH. Okay, so I have an expression now that is the Nernst equation that incorporates pH for a given expression. Obviously, you won't always cancel 2's because it won't always be an exponent 2 and it won't always be an n equals to 2. But on this specific example, the 2's did cancel out. So let's have a look at what this all means. So several slides later, we left off with this equation. The voltage under non-standard conditions for this equation, this part of the Krebs cycle, is the voltage under standard conditions minus RT over F log 10 multiplied by the pH. If we solve for RT over F log 10, so this is the constant part of our expression. So the dynamic thing is the pH, but the RT, the F, and the log 10 we can calculate. Then R is 8.314. We'll look at the units in a second. The temperature is in Kelvin, so 298. And Faraday's constant is 96485. Now, if we look at the units of that expression, that would give units of joule per coulomb when all is said and done. And then we've got log 10, which has no unit. Okay, so if we just plug in the numerical values of R, T, we're assuming 25 degrees Celsius. F, and typically, unless stated otherwise in general chemistry, you can always reasonably assume 25 degrees Celsius. Obviously, if this were an in vivo type of experiment or in vitro, you would probably assume 37 degrees, but in the regular general chemistry environment, let's assume 25. Then if we multiply this through, this will give you 0.0592 joule per coulomb. Okay, so what does that mean? Now that we know what this constant means and we have the expression from whence it came, it means that each increase of 1 pH unit, because we have to scale this by pH, is going to decrease the voltage by 0.0592 joules per coulomb. Joule per coulomb, we know, is just volt. So a joule per coulomb is equal to a volt. Or we could say 59.2 millivolt. So that's what it means. So not only have we seen that there is a pH sensitivity to voltage, or voltage is pH sensitive, but we can actually quantify the sensitivity for a given system. We've got our expression that contains pH in our Nernst equation. We can solve for the constant values, in other words, everything except pH. So if we look at our correction, we can see that the voltage differs from the standard via this correction. The correction has pH in it. The greater the pH change, the greater the correction, and the greater the loss from the standard value. So this is something that you would have to take into account in a medical application or in a non-medical application where there's pH sensitivity or there's a pH change during your process. In the second example, we've got another biologically relevant example. We have nicotinamide adenine dinucleotide, which is a coenzyme involved in stage 3 metabolism, just like the previous equation was in the Krebs cycle. So here, essentially, we have an oxidized coenzyme, hydronium, 2 electrons to get the reduced form of this coenzyme, and water. And we're told that the standard voltage for this process is negative 0.11 volts, but what's the non-standard voltage? Okay, so we're going to have to use the Nernst equation. So we know that E is E standard minus RT over NF log Q. There's our out-the-box Nernst equation. And on this occasion, we know that the reaction quotient is the product of the products minus divided by the product of the reactants. But we're interested in pH effects. So ultimately, we're interested in the things that change dynamically, which in this case would be hydronium. So in this case, our hydronium is a product, so it's going to be 1 over hydronium. And notice it's only first order in hydronium because there's a coefficient 1 here. Okay, so this means that we have the non-standard voltage is equal to the standard voltage minus RT over NF log 1 over hydronium, where I've just inserted Q into the Nernst equation over here. Well, I can incorporate my log base change, so convert from log base E to log base 10, and therefore I can use pH. So I can say that E is equal to E standard positive, because ultimately I'm going to invert this, so I'm going to change the signage of my log. So I've got plus RT over NF, and then I can have, instead of log X, I can have log 10, and then I can have log base 10, the inverted fraction. Okay, I inverted, I induce a negative, the negative cancels that negative and makes it positive. But ultimately I want to go back to negative again, because rather than positive log base 10 hydronium, by definition I want negative log base 10 hydronium, which is pH. So recall pH by definition is negative log base 10 hydronium. So I'm going to have the negative instead, which is going to go over here. So E is E standard minus RT over NF log 10 pH. So I'm now going to clear the board, plug some values in, and see what we have. Well, actually, we can probably continue a little bit in this space here. Notice that my N, similar to the last example, is 2. So I can calculate the constant parts except the pH. So I know that RT over NF, where N is 2, F is Faraday's constant, log 10, which is just a number. Well, I know that this is equal, if I convert this to volts, this is going to be equal to 0.0296 volts, or joule per coulomb, or volts. Okay, now I will have to clear the board and continue identifying what this all means. Okay, so in the previous board, we had our variant of the Nernst equation with our pH for this particular expression. And then we solved for the non-pH constant part of the expression. So RT over 2F log 10 was this number of volts. So we can clearly see that our voltage under non-standard conditions, which is our, pardon the pun, charge in this question, is E standard minus this correction, which is our 0.0296 volts pH. So we can see, let's say for example, at pH equal to 7, which is close to physiological pH, so the pH of on average biology. So a physiological pH, E is equal to the standard value minus 0.11 volts minus 0.0296 volts, which is our correction value, multiplied by pH 7, which has no units. And that would give us an E equal to negative 0.32 volts. So in the previous example, we interpreted what the value meant. In this example, we've selected a pH value, physiological pH, and we've actually inserted it in and seen how we can actually quantify the E, the non-standard voltage, given a certain pH. So clearly, because pH is in the equation with voltage, we have this pH sensitivity to voltage, and this is an extension or an application of the Nernst equation under pH varying conditions.